I am Çağrı, and Kubilay is my PhD supervisor. And today in my presentation, I will talk about the advances in multigraph neural networks. So it will be a bit technical. So this is the outline of my talk. I will first start with the motivation on multigraph neural networks. I will sometimes repeat what Kubilay said, and then I will talk about what are the limitations of the existing solutions for the multigraphs. And then I will present our proposed solution, MegaGNN, and towards the end, I will share our experimental results. So let's start with a simple definition. So in the figure, we see a simple graph, and the simple graph is a graph where there's only one edge is allowed in between the two nodes. So this graph could be directed or undirected, and it could also have some node and edge attributes. But in this talk, we are mainly interested in the multigraphs, where there are more than one edge is allowed in between the same two nodes. And this kind of graph is a key example of this graph is a financial transaction network, as Kubilay mentioned, because there could be multiple transactions between the same two accounts. So in the recent years, there has been a lot of progress happened on the graph neural networks, but their primary focus was on the simple graphs. Although they can be applied to the multigraphs, they are simply not effective and they have some limitations. So in the recent years, there has been also some GNN-based models are developed for multigraphs, namely ADAM and MultiGNN. And after a couple of slides, we will also be discuss what those models are and what are the actually limitations of them. So before moving on, I would like to also talk about the differences between the multigraph and the multirelational graph. So the multirelational graph has distinct edge types. Multigraph, on the other hand, is kind of more general because it doesn't have any explicit edge type definitions. So we can even say that the multirelational graph, in fact, a special case of the multigraph because we can make the transformation between multigraph and multirelational graph so that we can transform it by assigning different types on the edges of the multigraph. So the research on those two topics have been orthogonal mostly, and people were considering one or the other domain. So in this talk, our main focus will be on the multigraphs. So we will not be dealing with any explicit edge type definitions. So let's now review the existing solutions for the multigraphs. So the first solution is the ADAM. What it does is that it transforms the multigraph into a simple graph. So with an example figure, what they do here, we have a multigraph on the figure, and what ADAM does, they flattened all the multi-edges in between the same two nodes into a single edge representation. Thereby, they created this simple graph from this multigraph. And the subsequent GNN layers or the subsequent message passing layers will operate on the simple graph, and they perform the downstream task. However, the main limitation of this kind of approach is that they lose the original topology of the multigraph. In the flattening stage, they actually lose the original edges of the multigraph. So after several layers of GNN layers, they cannot produce the embeddings for those individual multi-edges. So as a result, those solutions are not effective on edge classification. So again, you can make a classification on this flattened representation, but then it will be the same prediction for all those multi-edges, and it will not be as effective. And the second model that I would like to discuss is the MultiGNN. Also, Kubilay mentioned it. So I will briefly again remind you what the MultiGNN is. So it introduces 3 multigraph adaptations on the base GNN model. So the first one is the reverse message passing. So I will explain it with an example. So we have an example graph on the figure, and the reverse message passing adds the reverse versions of the edges into the graph, and then they perform the message aggregation for incoming and outgoing neighbors separately. So as again, Kubilay mentioned, this improves the expressivity of the models because it allows for the computation of alt degrees, for example. And the second adaptation is ego IDs, where they mark the center nodes to detect the cycles in the multigraph. And the third adaptation is the multigraph port numbering. And the main purpose of doing this port numbering is actually to distinguish between the edges from the same neighbor and the edges that comes from the different neighbors. This is particularly important in multigraphs because, as we said, there are multiple edges in between the same two nodes, and a node should have to know the origin of the edges that comes from it. So in the gray node, it assigns port number 1 to the first neighbor and assigns the port number 2 to the second neighbor. So that in the message passing, when we use those features in the edges, this gray node can detect which edges comes from which neighbors, basically. However, the main limitation of this model is that this assignment of port numbers is arbitrary. There is no notion of order in the graph. So the assignment of those port numbers becomes arbitrary. As a result, this breaks the permutation equivalence property of the Bayes GNN model. So in the end, it makes the inconsistent model predictions under arbitrary permutations of nodes and edges. So as now we discussed what are the limitations and what are the existing solutions, now I want to present our own proposed solution, which is a mega GNN. So the mega GNN is a new message passing framework that we developed for multigraphs. And we introduce a two-stage message aggregation scheme inside the message passing framework. And our model can extend any baseline GNN model as the multi-adaptations. We can turn the GIN or PNA type Bayes models into models that can work effectively on multigraph settings. So now let's briefly remember what those models are. So on the right, we see one layer of GIN, and on the left, we see one layer of PNA. So as you know, the main idea is to update the embeddings of our target nodes, and in the next layer, we can work with the updated node embeddings. So we do this update by getting messages from the neighboring nodes. And those messages are first aggregated with an aggregation function, and then after a series of operations, we obtain new embedded features for our target node. So when we look at those two different architecture, we see that the main difference actually stems from the aggregation function. While the GIN uses the sum, the PNA uses different aggregation functions at the same time. So as you know, this aggregation function is a lossy operation. In the PNA, for example, they try to extract as many statistics as they can. So in our multigraph solution, we also aim those aggregation functions, and we try to make this aggregation in two stages to better exploit the inherent structure of the multigraph. Now, again, we can also use a learnable aggregation function with our method. Instead of sum, we can also use like generalized aggregation functions. And we will see the results of all of those methods in the experimental results. So now let's see how we do this two-stage aggregation on multigraphs. So in the figure, we have an example multigraph. There are 3 multi-edges between node I and j. So in order to perform the message aggregation in 2 stages, what we do is we introduce artificial nodes into our multigraph. So for example, in between node I and j, we introduce the artificial node Vij. And we do this for all the unique node pairs in our graph. So after this step, the message passing actually happens in 2 stages. So what we do is we first aggregate those multi-edges in the artificial nodes. And then in the second stage, our target node receives information from those artificial nodes. So by doing this kind of modification, we can actually address the limitations of the previous models. For example, we can preserve the topology of the original multigraph. We do not lose those original edges. And since this is a message passing based model, also this is a permutation equivariant. So let's see why this 2-stage aggregation makes sense. And I'll try to explain it with an example. On the figure, we have an example graph on the left with 4 edges. And there are 2 multi-edges between I and j. And there are 2 multi-edges between k and j. So in the 2-stage aggregation, as I said before, we first aggregate the multi-edges, and then node-level aggregation will be performed in the second stage. In the single stage, all the edges will be aggregated at once without distinguishing the sources of those edges. So actually, what is the advantage of doing this kind of two-stage aggregation? So assume that we have a Bayes GNN model that supports the sum and max aggregations. So with the single stage, we can calculate the sum of the elements or the maximum of the elements. In the two-stage, we can also calculate the same things. However, we can also calculate more different statistics from the neighbors. So for example, we can calculate the maximum of the sums that originates from different neighbors. So this two-stage becomes particularly important on financial applications because we can capture edge statistics per neighbor. For example, we can detect the maximum sum of payments per sender so that we can reveal their total contribution in financial transaction networks. So now I hope I can convince you that this two-stage aggregation makes sense. But until now, we haven't taken into account the direction of the edges. So as we see also in the multi-GNN, the reverse message passing is actually enhancing the model expressivity on directed multigraphs. So learning from that, we also add support to the reverse message passing with our multi-edge aggregation. So how we do it? We again similarly add the reverse versions of the original edges, and we also add those new artificial nodes. And then the messages from incoming and outgoing neighbors are separately aggregated so that we can compute the out degrees of the nodes as well. So for the properties, as I said, our mega GNN is a permutation equivariant because it's a message passing based model. And in the paper, we also show that our proposed model is universal, but there's a condition for that. So if there's a strict total order on the edges, then we show this is universal. And we can establish this order on the financial networks in the form of timestamps if they have high precision, for example. So how about in comparison with the multi-GNN that Kubilay talks? They were not permutation equivariant, and they also show that their model was always universal. So now let's see the experimental results. We conduct experiments on two different data sets. The first is the anti-money laundering, and the second is the ETH data sets. In the first one, our task is edge classification, and in the second, we have a node classification task. In the table, we see the statistics of the data sets. Again, as you can see, the data sets are highly imbalanced. And for the baselines, we consider three different GNN models: GIN, PNA, and GenAg. And for the baselines, we compare our mega adaptations with three different baselines. The first one is no adaptations. We directly use this GNN model with multi-adaptations of multi-GNN and also with the Adam adaptations. So now let's see our main results. In the graph, we see the AML edge classification results. And on the y-axis, we show the F1 score. And on the x-axis, we have three different GNN architectures. And for each of those architectures, we compare against no adaptation, meaning directly the GNN model itself, with the multi-adaptations and with our proposed mega adaptations, which is the two-stage aggregation scheme. So when we look at the graph, we see that we consistently outperformed both the no adaptation and the multi-adaptations in all data sets. And also it's important that we improve the scores in all of these different Bayes GNN architectures, which shows that our two-stage aggregation is rather it's a more general approach that can better exploit the underlying multigraph structure. So the only point where we have a slight decrease compared to multi is on the large HI data set on the GIN model in here. And we can see that we have a very high variance on this point. So it's not the most statistically significant result. And also this could kind of expect it, because as I showed you before, the gene model was using the sum aggregation function, and doing sum in the 2 stages doesn't make that much difference. So now let's see the ETH node classification results. This is the only benchmark we can compare against Adam. So Adam was transforming the multigraph into a simple graph before any GNN layers. So their results were not that consistent because this transformation actually makes the learning a bit harder. So when we compare to the Adam, we actually consistently deliver over 20% higher performance. And when we compare on the multi-adaptations on this ETH data set, we see that we can surpass them on the Gene and GenAg architectures, but we match their results on the PNA case. So you might be wondering, since we are adding an additional step into the system, what is the computational overhead doing this 2-stage aggregation? So this figure shows that. So we compare against the multi-PNA with our mega PNA, and also we included the mega PNA, but without the reverse message passing. And the orange line also shows the F1 score of the corresponding methods. So on the left, we see the throughput, which is transactions that we process per second. And on the right, we have the F1 scores. So when we compare to the multi-PNA and mega PNA, we see that our computational overhead is actually very minimal. So it's less than 5% on AML datasets and less than 10% on ETH dataset. And it's when we disable the reverse message passing, we can boost the inference performance. And we can also realize that on the AML dataset, we have a favorable speed and accuracy trade-off. As we disable the reverse message passing, we still get much better results, much higher accurate results with much higher inference rate compared to the multi-PNA. So actually, that's all I want to say about the experiments and for the conclusions. So with this type of proposed model, we address the shortcomings of the existing methods. So we first preserve the original topology of the multigraph. And secondly, we retain the permutation equivariance property. And on the data sets, we see improvements up to 11% over the multi-GNN. And on the ETH, we see more than 20% over Adam, and we match the results of multi-GNN. So you can read our paper from the archive link, and thank you so much for listening.